Evening, everybody. It's 5 o'clock on Tuesday. So, hi, John Paul. It is time for some Calc 2. All right. So, just a couple quick reminders, and I'll remind you at the end of class. Next week is our exam week. Tuesday will be a bit of a review day for any questions you want to ask. And the exam just needs to be taken by Friday of next week. We will have I'll have a proctoring session during our class time next Thursday. So not this Thursday, but a week from Thursday, for anybody who wants to do that via Zoom. But you can also use ProctorU. So that'll be available to you as well if you'd rather take it at a different time. Anytime next week that they're available. So I'll bring that up again at the end of class. And then if you guys have any questions about that, you always let me know. But let's get into this final topic, for the midterm and this module. So we also have the module quiz coming up. So 6.4 is another application of integrals. In this case, applications to physics, specifically about work and work done of moving an object, and also force of a fluid against a surface. Okay. And when we talk about work, we're talking about the physics definition of work. So let's just start off with that. And the PowerPoint, was in the invitation if you want to download it. Okay, so we're using the physics definition of work, not our intuitive sense of work. So the physics definition of work has a very objective definition, and that is the work done is the force times the distance. All right. Now, one of the things that's going to come up in this section, we started to talk about this a little bit on Thursday, is units. All right. I want you guys to get familiar with these units. Now, obviously, we're just seeing these for the first time today. So by all means, feel free to keep this table with you as we look through problems. Same table as in the online lesson. There's a couple reasons that the units are important. Number one is it lets us know if what we're doing is correct or not. And we looked at that a little bit last time to make sense of our problem. Do our units make sense? Same thing is going to happen here. So, you won't get this table on the midterm, for example, because some of the questions on the midterm are specifically going to ask you what are the units. So you do want to get familiar with these units for work, and then the units we'll use for force of a fluid. There's not a lot of them. And again, there's a lot of crossover with what we're doing in physics. And so what you want to take from this first slide is that, if we get something, and this is going to be how you identify a couple notable differences in the problems, and I'll point these out as we do some examples. Today is going to be very example heavy. Thursday is going to be a lot more time for us to work in groups. So in international units, a force is measured in newtons, the distance will be measured in meters, and the work, remember, is force times distance gives the work. So the multiplication of something in newtons with meters gives joules. In British units, the units we're more familiar with, a force is measured in pounds. And that'll be something that we'll look at in the problem. So when we have something in pounds, we already have force. The distance is in feet. The product of those is foot-pounds. So we'll look at how we can identify those as we go along. And it'll be something I point out to you that you're going to want to pay attention to, be very conscious of when you work on problems in the homework. All right, let's jump in and see what's happening here. We're going to start off with a very basic definition of force, which is that force is mass times acceleration. All right, nothing new. And I just have acceleration here represented as the second derivative of position. Now that's something you would have come across in Calc 1, right? The first derivative of position is velocity. The first derivative of velocity is acceleration. So acceleration is the second derivative of position. Now what we need to take from this is forces mass times acceleration. So first thing I'm going to is start with a very basic example that just gets us in this multiplicative state. So first off, if we wanted to know the work required to move a 5 kilogram mass up 10 meters, we actually don't need integration for this. And here's why. We're basically taking some 5 kilogram mass. Oh, shoot. Give me 1 second. For some reason, my pen is not writing at the moment. Sorry, guys. Having a technological issue for some reason. Give me 1 second. If not, we'll move to another. Okay. Give me 1 second. Example. So we want to move a 5 kilogram mass. And we want to move it up 10 meters. Now, here's the thing. Nothing's really changing in this problem. So all we need is the force of this mass. Thanks, John Paul, I appreciate it. It does happen to us all. All we need is the force of this object and then the distance. Now, 5 kilograms is mass. It's not a force, but as we know from here, force equals mass times acceleration, which is the 5 kilograms. And the acceleration is going to be the acceleration due to gravity. I mean, you'll just see me use G a lot in these problems. And when we do, G is 9.8 meters per second squared. So 5 times 9.8, which gives us 49. And remember, this 5 was in kilograms, it's a mass. Now it's a force, so that's 49 newtons. And now that we have the force to get the work done, we just take the 49 newtons, multiply it by the 10 meters, and the total work done is 490 joules. So now why are we looking at this? Because it's just multiplication. But remember, that's what integrals do. They sum up multiplicative structures. So what happens is, what's going to happen is the work is going to need an integral if we have a varying force. All right, so the situations we are going to look at, excuse me, are all going to have some kind of varying force. I'm going to point those out to you. So let's make this force vary. All right, so same 5 kilogram mass, except now it's going to decrease by 0.2 kilograms per meter. And that could be for a variety of reasons. You know, we'll look at one probably later. That's a leaky bucket. That's the same idea. All right, so let's see how we can approach this in a way that kind of makes us think, all right, now a definite interval is going to make sense for this. All right, so now We still want to go up a total of 10 meters, except now we're going to look at it as a slice. So say our mass is right here. This is our ith slice. And it is some x sub I from the top. All right, so that would make this distance here 10 minus x sub I. All right, so what our goal is going to be is to find what it takes to move this mass of the ith slice. Let's just say we want to move it a distance of delta x. All right, so some little arbitrary distance. And what we'll do is we'll sum up the work of going all the distances. Well, what we're going to do is we're going to work our way up. What do I mean by that? Well, let's think about it this way. We're going to start with the mass on the ith slice. It's going to look very similar to this, but now it's changing because the mass is different depending on where I measure. Because it decreases the mass as we're being raised, it's going to be lighter here than it would be down here. Now it starts at 10 kilograms. And then what's happening is we're losing a quarter of kilogram per meter. So minus 1/4. Now here's how we have to be careful about how our drawing is labeled. This is where we need to be consistent. All right, think about what's happening here. All right, it's going to be 10 at the very bottom, and it's going to decrease all the way to the top. So we've lost this part right here in mass. That's the amount of distance that we've covered for it to decrease. I'm going to write it again just because it's kind of messy on the other side. 10 minus x sub I. So this ith slice, what is its total mass? Well, it's 10 minus the quarter of kilogram per meter that we're losing over the meters it's traveled so far. All right, because I used x sub I for this side, this is 10 minus x sub I. That does not mean you have to label it this way. If you would have labeled this side x sub I and this 10 minus x sub I, that's fine. Final problem is going to come out exactly the same. So the most important thing when we're doing these diagrams is be consistent with your labeling. And we'll talk about that more as we do some more examples. Also, guys, as I go through these, if you have questions, let me know. Like I said, today's going to be more example heavy. So, I want to kind of invite some questions as I'm going through these if there's like a step that doesn't make sense. All right, now the next part is kind of nice. To turn a mass into a force, we just have to multiply the mass by acceleration. So F sub I is m sub I times gravity. Now, one of the things we could do is we could simplify this a little bit. You don't have to, but if you decided to, let's see. We distribute the quarter. The quarter of 10 is 2.5. So we'd have 10 minus 2.5, which is 7.5. And then negative quarter times a negative x sub I, so plus 1/4 x sub I. If you want to simplify, you do not have to. This is going to work just fine. So G times 10 minus 1/4, 10 minus x sub I. This is the force on the ith slice. Now our goal is to get work. So we want to get the work on the ith slice. Well, remember what we were saying. We were just going to try and move it delta x. So we're just moving it just this little bit, and then we're going to move it another delta x, another delta x. And we'll sum all those up with the definite integral. All we have to do to get the work on the ith slice is it's the force on the ith slice force on the ice slice times delta x. So gravity times 10 minus 1/4 of the 10 minus x sub I delta x. You're going to see me do a list like this on a lot of these work problems, and you get really used to it. This is where slicing becomes really helpful, because what we do is we simplify the problem and work our way up. Once we have the work on the ice slice, the variables match. We know that now we're going to calculate the work. It's going to be G. Remember, G is just gravity. I like to not put it in until the end because it's a constant. I'll do the same thing when we're dealing with densities. We just haven't gotten to one yet. So you'll see me do D or G and delta a lot in these. 10 minus 1/4, 10 minus x sub I. Now we go to the dx, because we've gone from the discrete case to the continuous case. The last thing we need are our limits of our integral. Remember, it shouldn't have a sub I in there, sorry. We don't need a sub I because we are in the continuous case. And the limits, remember that x is our variable. At the bottom, x is going to be 10. At the top, x is going to be 0. So we want to integrate from 0 to 10. Just like we've been doing in this module, I'm not going to calculate the value of any of the integrals for time's sake, because the goal here is getting them set up. That's the harder part. So the same thing will go today. But even though I'm not going to calculate the final number, one of the things I still want us to be focused on are the units. So notice this problem gave a distance in meters, a mass in kilograms. So if we were to go back to that table, distance in meters, mass was in kilograms, with the force in newtons, F sub I. This here would have been in newtons. Therefore, the work, this final answer, is going to be in joules. So once we compute this definite integral, that number would be joules. So this is our first look at a work problem. Now, a couple things I want to point out, and we'll see, see if there's any questions. Just kind of notice the difference between the black example and the blue example. Both of them featured a 5 kilogram mass. And both of them, I kind of did the structure from mass to force, force to work. Mass on the ice slice, force on the ice slice, work on the ice slice. That's going to be our build on a lot of these work problems to make them a little easier to deal with. What made us need the definite integral was a varying force. So all the rest of the work problems we're going to do today, and for module 6.4, or section 6.4, excuse me, is the fact that we have a varying force. So that's something you want to be looking out for. Okay, questions about this first example? And we're going to do more examples too. I've got a few picked out today. What I want to do is do some examples with you. Pause here and there for questions, or just so you can kind of see and talk you through the thought process on these. All right, let's look at the next one then. Okay. All right, so here's what's happening. We've got a force that varies from A to B. So in that last problem, the force of that object varied because its mass was decreasing. Again, think of a leaky bucket being raised. So we'll call that varying force f of x. What we do is we divide it into n subintervals. We look at the ith interval. because then f of x sub I is the force. We do this so that the interval is small enough so the force is constant. Then we get to work on the ice slice, is that times delta x. The work is about equal to the Riemann sum. We take the limit as n goes to infinity, and there's our definite integral. So it's the same idea that we've been propagating this entire module, this idea of slicing, looking at the contribution of each slice, adding them up with the Riemann sum, taking the limit as n goes to infinity, making it a definite interval. So I'm going to do slicing in a couple more problems, and then we might look at one or two problems where we don't do as much slicing because we've got the slicing idea. So what do we got next? This is a very, very common type of problem, these tank problems, emptying a tank. All right. So I find that the tank problems kind of lend themselves to a drawing. So a lot of times with the tank problems, I'll draw the tank. And we're going to look at a few variations of this one just to see how it changes our final answer. So 2 feet wide, 2 feet deep, excuse me, 2 feet in length, and then 3 feet deep. All right. Right now, we're assuming it's completely full, so that would be our water line right there. And we want to know what the work is going to be to empty the tank. Now, here is why this follows into our integral problem. Because as you empty the water, once the water gets to the top, that top slice of water no longer needs to be pushed up. If all we were doing was taking this 2 by 2 by 3, so 12 cubic foot block of water and lifting it up 3 feet, this would not need a definite integral. But because as we lift the water up, the water basically spills off over the top and it reduces the amount of volume we have to move out as we continue to move it up. That's what makes has this fall under a definite integral type work problem, because the force is varying. Okay. So what we want to do is we'll take all this water and we want to empty it. So let's talk about this as a slicing problem. So what we want to do is think about a slice. This is, as always, this is our ith slice. Right there. And we want to give that slice a value. Let's call it delta H. I'm not going to label anything else in the drawing just yet, because I want you to see, I want to give it a little motivation for what else we need to label in this drawing and what we don't. And it's going to vary from situation to situation, but our focus is now on this ith slice. Now, first thing I'm going to look at, because now we got a 3D problem going on. And in the problem before, we were given the mass. This time we weren't given the mass of this, so we got to kind of work up to it. And the first thing we're going to look at is the volume of the ith slice. And all we're looking at is this slice here, the purple filled in slice. It's basically going to have the shape of a square that's just got a little bit of height. So we have 3 dimensions. It's 2 by 2 by delta H. 2 by 2 by delta H. 4 delta H. Depending on how much time today, we'll look at some more interesting containers, like maybe a cone or something. We'll see how far we get. And guys, again, Yeah, if questions come up as I'm going through this, you want to pause me, you can turn on your mic and let me know, or shoot me a question in the chat. So we got the volume of the ice slice. Now, here's something that's interesting about this problem. Notice the units: feet, pounds per foot cubed. Okay, if I go back to our table, and again, you use this table until you get good at it. Feet, pounds, we're now in British units. And the reason this is important, British units, pounds are already a force. We do not need to multiply by gravity. If we have a mass is not a force. Take a force and make it take a mass and turn it into a force. We have to multiply by gravity. So that's one of the big reasons you need to know if you're in British units or international units. International units, you'll need to multiply by gravity, which is that 9.8 meters per second squared. British units, you will not, because pounds are already a force. And we'll do some in each, just to kind of go back and forth to give me an opportunity to point out, hey, look, we need G in this. Hey, look, we don't need G in this. But it's something we need to be cognizant of. So from the volume on the ice slice, we're going right to the force on the ice slice. Notice, and this is again where units can really help us out as to what's going on. Notice that the density of water, 62.4 pounds per cubic foot. Basically, what that's saying is if we take this and multiply it by volume, which would be in cubic feet, that's going to give us something in pounds. So let's kind of keep track of the units. This is going to be cubic feet. Now, to get the force on the ice slice, all we have to do is take the volume of the ice slice times the density. I like using this delta for density. Let's make a little note of it. Delta equals density, which in this case is the 62.4 cubic feet, pounds per cubic foot. Again, it's a constant. I'm going to save that to the very end of my problem, and you're going to see how it makes things a little cleaner. Now, multiplying these two together, I'm going to have 4 times delta, lowercase delta, uppercase delta. So I know I'm calling the same thing, delta H. And because now we're taking something that's in pounds per cubic foot times something that's in cubic feet. I don't need an equals there, excuse me. Our units would be pounds, all right? That checks out because this is a force. Our force should be in pounds. So a couple reasons that I stressed the paying attention to the units. One is it's something we should know, so we know what we're solving, but also it should make sense. This is a force. Our answer, we should be in pounds at this point. I'm going a little slow through these first couple examples. As we go through more, I'll probably go a little quicker. All right, force on the ice slice. We now need the work on the ice slice. That's the force on the ice slice times the distance traveled. Now here's how this works. All we care about is the distance that just this slice has to go to get out of the tank, which is this distance right here. Well, that is going to be H sub I, because it's different whether my slice is here versus whether my slice is up here or down here. That slice needs to go H sub I units to get out of the tank. Now, like I said before, we could make this H sub I, and then this would be 3 minus H sub I. Answer is going to come out exactly the same. So just make sure you're consistent through the whole problem. So taking that force on the ice slice and moving it H sub I out gives us the work on the ice slice. So we have 4 delta H sub I delta H. Now notice the variables match. Now, something I want to point out here is why the variables match. Notice delta H was a vertical measurement. It's just that thickness of our slice. H sub I is also a vertical measurement. So we would use this. We don't want to introduce another variable for this because they're in the same direction. This is going to be our variable, and this is going to be delta of our variable. Now, if we were going this direction on our slice and we wanted a widthwise, that's when we would have to get some relationship between the two variables. And again, I'm sure we'll do an example where we have to deal with that as well. And I'll make sure to point it out. All right. This is where you want to be. Oh, wow, I'm almost done. We've got the work on the ice slice. Oops. Which means to get to the work, all I have to do is drop the sub i's and turn this into a definite integral. The 4 delta are constants. If you want, you can put them out front. That's why I leave them that way till the end of the problem, because we end up with actually a really simple integral, h dh. And so the last thing we need are our limits. Well, the smallest possible slice is up here at the top, which is when h is 0. Our biggest possible slice is at the bottom when h is 3. And this will compute the amount of work done. And again, I like saving the 4 delta till the very end because it makes the integral a little bit easier to deal with. You do not have to. It's just the way that I like doing it. You'll see it, I do it in a lot of my problems. Now, right here, we took something that was in pounds, right? This was in pounds. Multiplied it by h, which is a vertical measurement, which is in feet. So the units on this thing are foot-pounds. The units on W sub I are the same as W, because this is just summing up all the work on each slice. So this final answer will be in pounds. Like I said, tank problems are really, really common. You're going to see a lot of tank problems in this section. Questions about this one? Okay, let's look at 2 different variations to see what would actually change and what doesn't in our integral. So this is a new problem. Same tank, same situation, but now we want to empty to a point 3 feet above the top of the tank. All right, let's change colors. Keep track of all this stuff. So now we want to go and get it out all the way up here to a point that is 3 feet above the top of the tank. All right, and let's kind of go through the steps and see what changes, what would change and what doesn't. We'd still do the same thing for our slice. So it turns out in this green version, let's call it, nothing changes as far as the volume of the ice slice. Well, to go from here to a force is the same. So the force on the ice slice would be the same. Here's where we're going to see the difference. Now, to get this slice out out completely, it has to go up h sub I plus another 3 feet. So that distance there is going to be 3 plus h sub I. So where it's going to finally change is the w sub I. Well, it's still going to have the same f sub I, but it's going to get multiplied by 3 plus h sub I. So when we go to create our interval for the work, it's going to look very similar. 4 delta. This now will be 3 plus h dh. And now here's the interesting thing. And this, this is going to take a little while to get used to. Remember what we're integrating over. We're integrating over h. H can only go from 0 to 3. So the limits actually don't change either. Now here's why this makes sense. This slice that's at the very top, it has to go 3 feet to get out. Well, that's going to be when h equals 0, because that puts our distance at 3. We can also look at it up here. H sub I is 0. We have the force on the ice slice times 3 feet. At the very bottom, when h is 3, well, that last slice has 6 feet to go out. 3 plus 3 is 6. So that's the 6 feet that that very bottom slice has to go. So the only thing that changed between this integral and this integral was the distance we had to go to get the work. Everything else was the same. Questions about that? Let's do one more variation. I don't have this on the slide, but it's worth looking at this variation. Let's say we only have 2 feet of water. We're not trying to go the 3 feet above, just 2 feet of water. We want to get it above 2 feet above. We just want to get it out the top of the tank. So the red version is going to be water is 2 feet deep. Okay. That slice stays the same. That force on the ice slice stays the same. And now to move that slice out, well, it's still h sub I. So it turns out that in this red case, the work on the ice slice stays the same. So it has the exact same integral, the 4 delta h dh as our first example. Here's what's going to change: the limits. Because what we're integrating over, or what we're slicing, is the water, not the tank. So now our top slice, which is basically my red top of the water here, to get that top slice out, it has to go 1 foot. So our lower limit is actually going to be 1 in this case. And h is going to go all the way to the bottom, and our upper limit is 3. Notice what the distance between the limits is. It's 2, which is the same as the depth of the water. So if we don't have a tank that's completely full, what I want you to really pay attention to is when you do your limits, remember that you're only integrating over fluid, not the entire tank if it's not full. If the tank is full, then it's the same thing, the fluid. And we could actually combine the two, right? And we could probably do it pretty quickly and see what color haven't we used. And maybe like a light green. I mean, if we wanted to do only 2 feet of water to a point 3 feet above, it's basically going to be a combination of the two. And we can not maybe do that, that's for sure. It'll just be a combination of the two. It'll still be the 1 to 3 on the limits for delta 3 plus h. dh. So this would be 2 feet of water to 3 feet above. Now, I'm doing this because I just want you to, because it's a basic example, because the square bottom of the tank makes it a little bit easier to deal with. But what I really want to point out, the reason I'm doing this is these are different variations of the same problem. go to 3 feet above the tank, only 2 feet of water when the tank is 3 feet high. I wanted you to see what part of the integral gets changed when that happens. When to go to that extra 3 feet, well, we just had to add it onto our distance. But when we only had 2 feet of water, it altered our limits. Questions about this example? All right. Like I said, I'm going through these a little slower because it's the first time through some of them. Want to talk. Next thing I want to talk about is force of the fluid. Then after that, we'll see what time we have left. But I'll hit a couple more examples, but I'll do them a little bit more quickly. And there's obviously examples in the lesson. You're going to have examples in the homework. So you're going to get a lot of practice with this. But I really wanted to point out some of the nuances. Okay, let's talk about force and pressure, and then I'll give you an example to help make this make more sense. So what we're looking at now is force exerted on a liquid, by a liquid on a surface. So we all have had experience in the water at some point, and we know that pressure of the water is varies with depth. Right? The deeper we go, the more pressure we feel. So what we're going to look at is how to take the pressure at a whole bunch of different points and sum it up to get the total force on the surface. And just to give you an idea of why this is important, imagine you're designing a surface that's going to go underwater, for instance, the window on a submarine, or the side of the below water side of a boat, or something that gets lowered into the water. It needs to be able to handle a certain amount of force over the entire panel or over the entire window, but the pressure isn't constant over the entire panel or window if they're vertical. So these are just some definitions. Pressure of a liquid is the force per unit area exerted by the liquid. It's equal in all directions at any given point, but it increases with depth. And that's where the integral is going to be involved, because we basically have a varying pressure. So one thing to point out, before we were looking at a varying force to calculate work. Now we're going to look at a varying pressure to calculate force, specifically of a liquid against a surface. So here's how we do this. It's a pretty cool little trick. This is if we're in international units. It's very similar in British units. The biggest difference, again, is whether or not you need to multiply by gravity. So at a depth of h meters, the pressure P is given by computing the total weight of a column of liquid h meters high with a base of 1 square meter. The reason we do that is because that makes the volume h times 1, which is just h. All right, so that allows us to really simplify this. So if the liquid has a density delta, then its weight per unit volume is delta G. Unless we're in British units, then it would just be delta. And so the weight of the column is delta G times H, because remember, H is the volume of the column. So we multiply by gravity to turn it to, so we got to multiply by the acceleration due to gravity, and the delta will give weight per unit volume. And I'll show you how this works in practice. I think it'll make a little bit more sense. Now, here's where the integral comes in. The force is pressure times area. If the pressure is constant, this is a very straightforward multiplication problem. And when it's not constant is when we need a definite integral to sum up over this multiplicative structure. So the units get changed up a little bit here. and we'll talk through these as well. So for the problems we're going to be working, pressure is measured in newtons per meter squared. Area then is in meters squared, so the force would be in newtons. In our British units, pounds per foot squared, feet squared, and pounds. Now again, when we're in British units, we won't need to multiply by gravity. International units, we will. And you'll know right at the beginning of a problem. Right here, feet, feet, feet. You see that? Oh, feet. We're in British units. We do not need to multiply by gravity. All right. Now, this we're going to do with water. I didn't put delta in this problem, but that's okay. Actually, we can do that. Let's do this in general. We'll do this for any liquid, because the nice thing is if we do it in general, once we find out the density for the liquid, we can always include it later. But I want to talk about two things: when we need an interval and when we don't, and how we can use slicing to solve this. So let's make our tank 5 feet wide. Four feet in length. So 5 feet, 4 feet. And I jumped ahead a little bit there. We got 3, it's 3 feet. And it's filled to 6 inches from the top. All right, so there's our water. Okay, like I said, you're going to see a lot of problems in this section that doing the drawing is very useful. Okay, there's 2 questions here. We want the total force on the bottom of the tank and the total force on the wider side of the tank, or the front of this tank. All right, so let's do the bottom first. Now, here's what's interesting about the bottom. At the bottom, which is basically down here, the water pressure is the same at all the points because they're all at the same depth. So at the bottom, what we need to look at is how deep we are. And that bottom is 2.5 feet deep from the surface. That's the H. So we have, let's kind of go through this. So the force is equal to the pressure times the area. The area of the bottom is pretty easy. It's just 5 times 4. So let's talk about the pressure. How do we get the pressure? So the pressure at the bottom, and let me go back to the previous slide so you can kind of see how these match up, because I know this seemed kind of arbitrary. Remember, we don't need gravity in this one because we're already going to get a delta that's going to be in pounds per foot squared. So the pressure is going to be delta times H, which is our depth. All the points of the bottom of the tank are all 2.5 feet from the top. So H is 2.5. Delta. This pressure does not vary. It is constant. So therefore the force is the pressure times the area. So 2.5 delta. And then that gets multiplied by the area, which is 5 by 4, or 20. So 2.5 times 20, so 50 delta. And the units on the force, remember this is a force. We are in British units. So it's going to be pounds. Oops, wanted to go to, sorry guys, went the wrong way there. We are in British units, our force is in pounds. Now, again, I didn't give you a delta for this problem. What's nice about this is now, okay, if it's water, we'll get the density of water and we'll plug it in and there's our answer. But if it's oil, we'll get the density of oil, we'll plug it in and solve our problem. So that's one of the reasons I like saving the density to the end, because it's just a constant. It doesn't make a difference on our multiplication. And it won't make a difference in our integral either. So the bottom, we didn't need an integral. Let's talk about when we do the wide side. And let's do this slicing route. Again, guys, when you get good at these, you may not want to use slicing too much. That's up to you. But I like it because what it does is, oops, we don't need that side, is it makes a big problem smaller. Now remember, when you're doing force of a fluid, we're just looking at area. So we're only looking at the force on this side of the tank. So my slice, well, I just need, this is my, this is my slice. And that slice has to have a thickness, let's call it delta H. And that slice has a depth from the water, not from the top of the tank. Remember, if there's no water up here, that's not contributing to the total force on the side. So always measure your H sub I from the surface of the water. You can also measure it from the bottom, that's fine. And then this would be the top of the water minus H sub I. So again, I can't stress that enough. As long as you're consistent through the whole problem, it's not a big deal. All right, let's talk about the pressure on the ice slice. The pressure on the ice slice. Now, pressure occurs at just a single point per area, per unit area. So we're like right here at this single point. The pressure at that point is going to be delta times H sub I. Now there's an area of the ice slice. This slice is the shape of a rectangle that has a width of 5, because it's a constant width, times delta H. And now the force on the ice slice is the pressure on the ice slice times the area of the ice slice. We basically multiplied these two together. Delta H sub I times 5 delta H. I like grouping my constants, so I like to put the 5 and the delta out front. And then H sub I, let's make that sub I a little nicer. H sub I, delta H. Our variables match. We're already at the force on the ice slice, which means we are ready to turn this into a definite integral. So the force is going to be, a lot of times I'll pull the 5 delta out of the integral, but for today, let's put it in there. Don't need the sub I on the H, dH. Last thing we need are the limits on H. Now, at the very top of the water, H is equal to 0. Now at the bottom, it's at 2.5 feet. And something to remember, and this is gonna, this will come up in some of the homework problems. Be consistent with your units. We want to be in feet. So if we were given, so like here, when we were given 6 inches from the top, we're probably better off at converting that into feet. So 0.5 feet from the top, which means the depth down here from here to here is from the top of the water to the bottom of the tank is 2.5 feet. And those will be our limits, and our force will come out in pounds. Now again, I left delta because we didn't get one in this problem. Not a big deal. We will save the delta till later, because then we can handle the density of any liquid, because it doesn't change the rest of the problem. So that is force of a fluid. Questions at this point? Questions about this problem, force of a fluid? All right, let's do some more examples. Change context a little bit. Let's see. Let's do one here. Hooke's law. Now this one, I'm going to show you where the definite integral comes in and why we need this problem. And this is a good one to talk about units as well. All right. So the force required to maintain a spring stretched x units beyond its natural length is proportional to x. Let k be the constant of proportionality. So if F equals kx, this is basically Hooke's law. Nothing crazy going on. What it tells us is that the force needed to maintain a spring stretched x units beyond its natural length is proportional to x. The same thing goes with keeping it compressed. This means we have a varying force. This varying force is what we're going to take care of with our integral. Now, here's where we have to be a little bit careful. All right, so the spring has a natural length of 20 centimeters. So let's say that that's the unstretched, uncompressed spring is 20 centimeters. What we know is that a 25 Newton force is needed to stretch it an extra 10 centimeters. So let's change colors for the stretched part. So we stretch it an extra 10 centimeters. Sorry, this isn't to scale, but you get the idea. So what's happening is we stretch it up to 10 centimeters. This is the amount of force. Now, here's something to remember. Remember that Newton's specifically deals with measurements that are in meters. So when we do this, we don't want to use centimeters. We want to use meters. So this would be 0.1 meter. This would be the 0.2 centimeters, excuse me, 0.2 meters. So that's what I was talking about earlier. We need to make sure we're consistent with our units. So if we were like on the other problem, where we were given something in inches, we want to think about it in terms of feet. In this case, if we're given something in centimeters, we want to use all these numbers in meters. So here's how this is used to get the formula for the force. So we know that 25 newtons is needed in order to pull this out 0.1 meter. So what's happening is the force required to maintain a spring stretched x units beyond its natural length. Excuse me. Its natural length was 20. We pulled it out to 30, which was only an additional 10. So that's why right here is just 0.1, not the whole 30 centimeters, because it's 20 natural resting length. It's pulled another 10. There's the 30. We solve this for K. This is going to give a K of 250. What that gives us is our varying force. Remember what we were talking about earlier. Why do we need a definite integral to calculate work? We need a definite integral to calculate work if there is a varying force. So to calculate the total work on this is going to be 250x dx. This is the distance. Remember when we looked at moving that mass up, we looked at moving it delta x. We're kind of doing the same thing here. We're moving it delta x by delta x. And then we want to know how much work is required to stretch it from its natural resting length of 20 centimeters out to 25 centimeters. Well, at 20 centimeters, we haven't stretched it at all, so that would be 0. And then we're pulling it out 5 centimeters, but we have to do it in meters. So 0.05 meters would be our upper length. Now, this is a work problem. This is in international units. So it would come out in joules. So I want to do some where we don't do the slicing, just because I don't want you to feel like you're stuck in this slicing box in this entire section. But I do think the slicing is really helpful to see how these things build from a small problem to a bigger problem. I want to make sure we did a Hooke's law so you guys had a chance to see it. Questions about that one? Oh. Okay, let's do another work problem. Oh, this is kind of a cool one. It's similar to something we did earlier, but I'll do it a little quicker and see what you think. All right, so what do we have going on? Got a leaky bucket that's lifted 20 feet into the air at a constant speed. The rope weighs 0.3 pounds per foot. The bucket starts with 10 pounds of water and leaks at a constant rate. There are 5 pounds of water left just as it reaches the top. How much work was done to raise the bucket, rope, water, all three together? All right, so this is similar to the one we looked at earlier, it's just a little bit more going on. So let's say here's our rope hanging down. Here's our leaky bucket. All right, so let's basically the bucket's going to be our ith slice. And we're going to look at 3 different things going on, but they all add up to give the total work. So we look at the bucket. We're going to look at the rope. And we're going to look at the water. Now the bucket. Notice the units, pounds, pounds per foot. We are in British units. We do not need to multiply by gravity. So let's just talk about the force on the ith slice. Well, on the bucket's 5 pounds at the bottom, the bucket's 5 pounds at the top. So the bucket, its force is just the 5 pounds. All these will be in pounds, so let's actually not put that there. We'll put it at the end. So the units on force, these will all be in pounds. Actually, let's clean this up a little. See a better spot. All right, so give me just a second. So we're going to think of the bucket as our ith slice. And this is going to be our F sub I, and it is measured in pounds. The bucket's 5 pounds at the bottom, bucket's 5 pounds at the top. It's getting raised 20 feet. So we don't need a definite integral to get the work done on the bucket. The work done on the bucket is just 5 times 20. So 5 times 20. Because it's the same weight it is here that it is up here, being raised up 20 feet. Now here's where things start to get interesting. The rope varies because as we pull the rope up, there's less of the rope that needs to be pulled up. So the rope has a varying force. And the water has a varying force because it's a leaky bucket. And we're running out of water. We start with 10 pounds, we end with 5 pounds. So these are going to vary. This is where things start to get kind of cool. And, we can label this either way. We can call this one X sub I, or we can call below our slice X sub I. It doesn't matter. We're going to get the same thing either way. Let's do X sub I there. Now remember, the whole thing is 20. So this is 20 minus X sub I. It doesn't matter which one you call X sub I and which was 20 X sub I. as long as you're consistent through the whole problem. All right. Now remember, this is our ith slice. The bucket is right here. We're going to be moving all, we're looking at, W sub I is all of it. How do we move that delta X? Well, that's 5. Delta X, well, when we move the whole distance, there's our 20. Let's talk about the rope. Here's our rope. We have X sub I feet of rope, and its density is 0.3 pounds per foot. So the weight of the rope at this given point is 0.3 X sub I. There's our varying force. Now that needs to get moved up delta X. So we have 0.3 X sub I, delta X. And now, as we've talked about before, all we need to do to get this into our definite integral, 0.3 X sub I dx. And X sub I is going to go from 0 all the way to 20. And guys, like I said, if you have questions as I'm going through these, let me know. At this point, I'm just kind of going through some different variety of examples just to give you some different exposure to see what kind of questions come out. All right, last thing is the water. So the water, we have to do a little bit of work on this one because we weren't given how quickly the water is draining, but here's what we know. There's 5 pounds left as it reaches the top. There's 10 pounds. There's 10 pounds at the bottom. So it goes from 10 to 5 pounds over the course of 20 feet. And it leaks at a constant rate. Now, what we know, and this is kind of similar to the rope, we need to know the change in pounds per foot, right? It goes at, at 20 feet. At the 20-foot mark, it's going to be 5 pounds. And at the bottom, it was 10 pounds over 20 feet. Actually, I don't want to put that right there. I'm going to need that space. All right, so the rate of, it's called rate of water loss. So we're losing 5 pounds over 20 feet. Well, that means we are losing 1/4 pound per foot. Excuse me. This is basically that changing, similar to the density of the rope. That's that changing density of the water. Now, you need to think about what the water looks like. So at the bottom, when we're down here, the water is at 10 pounds. Haven't lost any, but we're losing 1/4 pound every time we go up a foot. So what we need to do is figure out how much water we have at our ith slice. Well, how far up have we gone? We've gone up 20 minus X sub I feet. So we start with 10 pounds. We've been losing 1/4 pound for 10 minus X sub I feet. And once again, we could, oh, sorry, not 10 minus X sub I, 20 minus X. Now, once again, we can simplify this, but before I do, I want to make sure that this makes sense. We've gone up 20 minus X sub I feet, and we're losing 1/4 pound a foot. So that's what this part here is saying, losing 1/4 pound a foot times the 20 minus X sub I feet. We're starting with 10 pounds. If you want to simplify this, you can. you distribute the 1/4, so that would be -5. So 10 minus 5 is 5. And then -1/4 times a negative x sub I is plus 1/4 x sub I. So that might be easier to deal with going forward. We'll deal with the simplified one this time. But based off our diagram, based off the way I decided to label it, this is a way of setting it up. Okay, so again, all we have to do is multiply it by delta x, excuse me. So 5 plus 1/4 x sub I times delta x. And to get the work on this for the water will be 5 plus 1/4 x dx, and once again from 0 to 20. Now, I did each of these separate, and I did that on purpose because I wanted to examine each of them separately because there's a lot going on in this problem. But here's something I want to talk about is we could have done this all as a single problem. Okay. Adding those up will give us the total. I could have just as easily added them at the f sub I step. For the whole thing, we could have added them here. Or we could have added them here. So they all could go in the same definite interval. When we go to calculate the work, limits would be 0 to 20. And we could just basically take it from this step. 5 plus 0.3x plus, I'll put it in parentheses for note's sake, 5 plus 1/4 x dx. Because all of them have the same limits, 0 to 20, there's your 5 times 20. And then we see the other two definite integrals. We could simplify this a little bit, adding the 5 and the 5. 0 to 20, we got 10 plus 0.55 x dx. So after all said and done, this integral of just this linear function would give us our work done and our units for this, because we're in British units, is foot-pounds. Questions about this? There's a lot going on in this one, but that's why I chose it, because like I said, I really want to kind of push you guys to think about, what's varying, what's not. All right, let's see, what do we got? Now we got about 15 minutes left. We have time left for one more. Let's see, what would be, let's do an emptying the tank problem. That's maybe got a little bit more going on than the one we did earlier. And then we'll finish on that. I think we can get one. I think we can squeeze one in here in the last little bit. So not that one. Yes, right here. And we'll do this. Let's empty it to a level 2 meters above the top. All right, so we got a trough that has a triangular cross section. So what's going on? Here's our trough. And it is 5 meters high. It is 3 meters wide at the top. So let's put this back here so it's out of our way. And it is 8 meters long. Distance there. All right. This one is filled up to 3 meters with water. So it's not all the way full. So let's mark that. Let's do this. So that is only 3 meters. And we want to empty this to a point that is 2 meters above the top of the tank. So a really nice problem, a lot going on. And let's talk about how we slice and build to our final answer. So there's our well. It's not all the way full. All right, so first off, first thing I want you to notice is the units, meters, kilograms, meters cubed. We need to multiply by gravity at some point. It better be in our final answer, okay? Now, if we do a slice, there's my ith slice. Let's give it a thickness of, let's call it delta H. And we've got to come up with, first off, the volume of the ith slice. Well, the volume is this rectangular solid. But notice that this side, whether I take the slice here, up here, or down here, will always vary. That means it needs a variable, and it's not in the same direction as my delta H. So let's call it the width. Let's call it W sub I. All right, now I've got 3 dimensions. I can get the volume. W sub I, this length is 8, and regardless of where I take the slice, it's always 8. So that's why I don't need a variable for this side, and this is delta H. So I've got 8 W sub I delta H, volume of the ith slice. So we are going to have a variable issue that we have to take care of. Might as well get it done now because it's going to be there for the rest of the problem. You know, we talked about that first time we talked about slicing. So if we look at what we got, we do have similar triangles. Problem is we've only got the W sub I. All right, not a big deal. I'm going to change things up in this one because I want you to see that the way we label things doesn't matter. All right, so that's what that distance here from the tip of my triangular trough to my slice, I'm going to call H sub I. Because if I look at this triangle straight down, apologize for my messy handwriting, W sub I, H sub I, this is in a triangle that has a base of 3 and a height of 5. There is our similar triangles. It comes up a lot in this section. So what do we got here? W sub I is to H sub I. So width is to height as width is to height. We want to sub out W sub I and sub in H sub I. So if we solve this for W sub I, we get W sub I equals 3/5 H sub I. We're going to take that and plug it in here. So that's where this is going to go. So we have 8 times 3/5 H sub I. Oops, not going to do that. Delta H. And, you know, I always like to clean things up as much before the next step because it's only going to get longer. So I'm going to write that as 24/5 H sub I delta H. All right. So here's what we've done so far. We got the volume of the ith slice, and then we saw, hey, we got a discrepancy in variables, so we made them be the same variable. All right. Now let's go through the process. The volume of the ith slice. Well, let's see. We need to turn that into a mass. The mass of the ith slice is the density times the volume of the ith slice. Density is the 1,000. I'm going to save that for later. So I've got delta 24/5 H sub I delta H. These guys are just constants. They're going to be coming along for the ride. This is going to be the thing that makes the difference in the integral. All right. Force on the ith slice. Well, remember, it's mass times acceleration. So that's basically taking our mass on the ith slice and multiplying it by gravity. Gravity is just the 9.8 meters per second squared. Again, I'm going to save that till the end. I'll put a note here. G is the 9.8 meters per second squared. I'm going to save that for the end. Let's put in the let's take care of the integration first and then put in the constant. All right, so I've got a couple constants. I've got a few constants in here. I'm going to write them this way. You guys can tell me what you think. 24/5, that's that. Delta G H sub I delta H. All right, this whole part here, I know it looks like a big mess, but this is all constants. This is 1,000, this is 9.8. If you want, you could put them in now, multiply everything together. I like saving them to the end because you always want to try and minimize round. And as are, these are nice exact numbers. I can put them all in my calculator at once. All right, here's the next step. Work on the ith slice. Well, we know that's the force on the ith slice times the distance to get it out. All right, so we got to be a little careful here. This is H sub I, but it has to be in terms of it. The distance to move this slice, well, how far do we have to move it? We have to move it all the way up to here, right? Because we want to get it that 2 meters above. Well, I know from the tip of the triangle to up to here, we know from here to here is 5, and here to here is 2, right? So this total distance is 7. So I have 7, but I'm subtracting off the H sub I. So the distance that I need to move my slice is 7 minus H sub I. And that's how we use our diagram to get these values. Again, I changed up the way I measured the H sub I. And I did it intentionally because I just want you to see it doesn't matter which I label. I could have had the H sub I been from my slice to the bottom of the triangle. It's all going to come out the same in the end, as long as you're consistent through the whole problem. Okay, now I'm going to kind of keep things in order. What I mean by that, I'm going to keep the constants at front from the F sub I, which is the 24/5 delta G. I have the H sub I, and then 7 minus H sub I delta H. Guys, this is our integrand. Once you have W sub I, you have your integrand. So when we go to write up the integral for work, I'm going to put all of these constants out. 24/5 delta G. Those are just numbers that I'll multiply my integral by at the end. H, 7 minus H, dH. We are good on everything. We just need our limits. And so when you go to do your limits, here's what you want to remind yourself. What's your variable? H. Where is H in your diagram? H is the distance from the tip of the trough, or basically the bottom of the trough, or the bottom of the water, or I think it's water, yeah. So that means the lowest H can be is 0. Well, let's make sure that that 0 makes sense. We just want to, it's just a quick check to make sure 0 makes sense. When 0 gets put in for this H, our distance is 7. Well, if we're at the very bottom of the tank, it's going to be 7. I think I might have called it 7. Sorry, it's going to be 7 meters to get out of it. So the 0 makes sense. Now we're integrating over the water. So H is only going to go up to here, right? We don't want to go to the top of the tank because the tank's not full. And the water's only 3 meters deep, so H is going to go from 0 to 3. There is the definite integral that will give us the work done in emptying this tank to 2 meters above the height. Now, once we're done with this will be in joules. But had we labeled the H a little bit differently, like let's say we had done the H from here to here, our limits would have looked a little different. So all these things coordinate depending on how you decide to label your diagram. because there really is an infinite amount of ways to write up this integral that will come out correct. But based off of the way we normally do the diagram, there's probably only 2 or 3 possible iterations we're actually going to see. And depending on whether I label my h from the bottom to my slice or the top to my slice, well, that's going to affect the way the rest of the problem looks. But it will still give you the same value for the work done. Questions about that one? All right. Then I'm going to stop there. This is what I wanted to accomplish. I wanted to go through some of the basics very slowly in the beginning so you can see where this stuff was coming from the online lesson. And then I wanted to do a couple of examples that change the scenario up a little bit. Hooke's law, the raising the bucket when it's a leaky bucket, and you've got the rope changing, not the rope changing, but the weight of the rope's changing because as it's getting pulled up, you have less rope. And I wanted to do another one where we're pushed a little bit more like this trough problem. That's what I wanted to do for today, just to give you guys some different looks so you can kind of see the thought process in setting these up and we could talk through them. Thursday, what we're going to do is I might do an example or 2 at the beginning, but probably not much. Thursday, we're going to spend more time. I'm going to let you guys work on some problems. I have a worksheet, which let me put it in chat in case you want to play around with it at all. You know, I have a worksheet that we might work on, or we might work on some. If some of you guys want to start the 6.4 homework and work on a couple of the problems from homework in groups, that's fine. Because there's so much going on in this section, I like to take 2 class periods to go over it, make sure we understand it. So Thursday is going to be a little bit more, a lot less of me talking and a lot more letting you guys work in your groups, chat, just really get the hang of these kinds of problems because you have the module quiz coming up for module 6 soon, and these are going to be on the exam next week. So Thursday will be kind of a chance to recap the stuff in 6.4 and any of the other sections in 6 that we have questions on. And then a week from today will be review, meaning you guys can come to class, any questions you guys want to ask, let me know. What I always